Good morning, all participants. We will be starting our session very soon. Good morning, participants. Today's session speaker is Dr. Ram Pilas Pachori, sir, from IIT Indore. Good morning, sir.
Good morning, Mrs.
Yes, sir. So we welcome you on the behalf of NIT Raipur family. We are very honored to have you with us today for this session. So, Dr. Ram Vilas Pachori from IIT Indore. Sir has done his PhD from Indian Institute of Technology, Kanpur in 2008. He has also worked as a postdoctoral fellow at Charles Technique Institute, University of Technology of Troyes, France during 2007-8. Currently, he is working as a professor in Department of Electrical Engineering at IIT Indore, India. His research interest includes biomedical signal processing, speech signal processing, non-stationary signal processing, computer-aided medical diagnosis, and signal processing for mechanical systems. He is an associate editor of Electronic Letters, Biomedical Signal Processing and Control, IEEE Transaction on Neural System and Rehabilitation Engineering Journals, and an editor of IETE Technical Review Journal. He is also a senior member of IEEE and a fellow of IETE and IET. He has supervised 14 PhD, 20 MTechs, and 41 BTech students for their thesis and projects, and has more than 234 publications, which includes journal, conferences, books, and books chapters. He has delivered more than 160 talks in various conferences, workshops, short-term courses, and institute. So today, Sir will be covering the topic Intelligent Computing for Brain Health Application in Detection of Epilepsy. So thank you, Sir. Now I would like to request our coordinator, Dr. Mridu Sau, to welcome Sir.
Yes, good morning, sir.
Good morning, Mrs.
Yeah, on behalf of NIT Raipur, sir, I cordially welcome you, sir, in our session.
Thank you very much. Thank you.
Yes, sir. Sir, could we start your session, sir?
Yeah, and thank you very much for nice introduction. And good morning to everyone. And I would like to convey my thanks to Professor Midhu Sahu and Professor Vikesh Singh, course coordinator of this faculty development program on intelligent computing in healthcare, for providing me this opportunity to deliver a talk in this FDP. Thank you very much for this opportunity. Let me share my talk.
Gitika, please off your camera. Gitika, are you there? Gitika, a participant, Gitika, please off your camera. Samriddhi, kindly instruct him.
Yes, ma'am.
Yeah, are you able to see the slides?
Sir.
Yes, sir.
Yes, sir, it's a visit. Yeah.
So thank you very much. Good morning to everyone. So today's talk is on intelligent computing for brain health with some applications. It will also cover epileptic seizures, and it will also have this sleep stages detection and detection of human emotions based on the EEG signals. And this electroencephalogram, they are also known as EEG signals. Actually, they are very useful to understand the behavior of the human brain, understand the state of the brain, understand the normality, abnormality of the human brain, and what generally neurologists or doctors, they perform visual inspection of EEG signals in order to perform diagnosis, and such kind of procedure has actually a lot of problems that we will see in this talk. And due to these reasons, there is a lot of interest in the literature to apply signal processing and machine learning together to develop automated systems, so which can be used for to design the intelligent system or intelligent computing for assessment of the brain health. And there are many disorders which include stress, anxiety, depression, Parkinson disease, Alzheimer, epilepsy, sleep disorders, human emotions disorder. So in all these actually these diseases, there is a lot of applications and a lot of use of these intelligent computing systems. And in this talk, we will see use of machine learning methods, say signal processing techniques, for designing such intelligent systems, such expert systems, such automated systems, which can detect automatically the state of the human brain. And these systems that we develop with the help of the signal processing machine learning algorithms, they can be used nicely in the form of software in the computers, laptops, and mobile smartphones, and in that way this smartphone will become really smart. So these are actually these are the some directions of this kind of research. And we will also actually see the use of signal processing. Signal processing is a very actually nice set of techniques which help us to define a good set of features, and that set of features can be used as diagnostic features, can have interpretation of the disease, brain related disease. And then we will actually we will apply machine learning algorithms which will use these generated features or extracted features, obtained features from the signals in order to develop automated classification. So with this background, let us start this talk. So this is the overview of this talk. First we will see introduction, then in the motivation for the introduction, motivation for studying this work, and what is the EEG signal, and why we need intelligent systems or intelligent computing for analysis and classification of EEG signals. And then we will see use of empirical mode decomposition for obtaining features for analysis of normal and seizure EEG signals. And these features also will be used for the classification of seizure and non-seizure EEG signals. And then these features will be actually applied for the detection of epileptic seizures using EEG signals. And after that, we will see time frequency image based features for classification of sleep stages. So we will also actually in time frequency distributions, this is also one of the tool or set of techniques which are suitable for analysis of non-state signals. And this time frequency distribution represents the energy of the signal as a function of time and frequency, and that energy is positive quantity, so we can convert into image where intensity is also positive. So that time frequency image that is formed from the time frequency distribution can be used as a actually platform to extract the features, and these features can be used for the classical sleep stage that we will see in this part. And after that, multivariate decomposition based features for human emotion classification will be explained, and the end conclusion will be provided. So human brain actually is a very highly complicated and nonlinear system, and whatever it is very difficult to understand, and whatever we understand this brain, it is actually very useful. So for example, you have recorded EEG signal in the morning time during happy emotion, and if you record EEG signal same after maybe after 2 hours, 3 hours, and the signals will not be same during the same emotion, same state of the emotions. Are you able to hear me?
Yes, sir.
Okay, thank you very much, thank you. So this actually these signals have actually a lot of variability, and like even if you have you perform various trials, for example, you record 10, 12 EEG signal at a time, and with the different trials, then also they are not similar. So there is a lot of variability in the signal, and they are also generated from the highly nonlinear system. And this EEG, which is actually which is the full form, which represents electroencephalogram, and that actually measures electrical activity of the brain, which is generated by the neurons inside the brain, and that is actually that is assessed with the help of EEG signals. So EEG signal is a very useful tool for investigating different physiological and pathological states of the human brain. And if you have any problem related to the brain disorder or brain abnormality, if you go to doctor or neurologist, they will actually suggest go for EEG signal. And that is the EEG signal is actually a tool to our first signature that we use for the assessment of the this brain disorders, or obtaining the information related to the these physiological and pathological states of the human brain. And what we want, actually we want to use some algorithm, and we want to perform some quantitative analysis of EEG signals in order to understand these variability, these abnormalities. Then actually that is very challenging task, because these EEG signals, they are very complicated, and they are irregular nature. They look like chaotic signal, and they are very complicated. And even like if you see the signal for very low scale, there is no trend of the data. There is no it doesn't appear that it will follow some rule. So due to that, actually it is very difficult to model the EEG signal. And the EEG signal comes under the class of non-steady signal. So like in signal processing, we use mathematical models to represent the signal, and if any parameters of these models change with time, then we call it non-steady signal. And it has been shown in the literature, like even for this EEG signal, if you limit EEG signal for very small interval of time, very less number of samples, then also it is found to be non-stationary. So due to these reasons, there is actually a lot of challenges to perform this quantitative analysis. And what generally doctors do, they perform visual scanning of EEG signal. So like if you go to hospital, doctor will record your EEG signals, and then it will be printed on the paper, and then they perform visual scanning. And that actually that is very time consuming. For example, the patient may be suffering from epilepsy, and it has seizures, and seizures, the recurrence, repetition or repetition of the seizures, and that is epilepsy. And it can be sleep disorders, it can be anxiety, depression, so so person has to be admitted in the hospital, and for example, or admitted for 12 hours. In that scenario, it is very difficult to monitor it. You take printout, or you keep monitoring the changes in the signal, because patients are many and doctors are less. Doctors are only one or two, and so it is very difficult to perform this kind of visual scanning for a specific patient. And this method, actually the visual scanning of EEG signal may be inaccurate also. So, and it is also very complicated, like monitoring say signals for particular patient. It is very complicated task, and it is subject to judgment and suffers from human error. For example, you must have heard when you in the hospitals, like people say this is the person is diagnosed with the epilepsy, and let us have another opinion. So that is actually the patients, they want to have different opinions. So this whatever diagnosis procedure that we perform for this actually based on the EEG signal, that based on the recorded EEG signal using this visual scanning, that is subjective in nature, and it suffers from human error. And generally, this visual scanning of EEG signals, that is performed by the trained professionals. And due to these reasons, this is actually there is a lot of interest in the literature to develop these automated methods which are based on the signal processing and machine learning techniques, and where we can extract the suitable features, and these features can be associated with the level of the disease and type of the for example, epileptic seizure. And if you can associate that feature with the disease, then it can be used for the diagnosis purpose by the common people. So due to that, actually due to these problems in literature, there is a lot of actually now interest to develop various features, various analysis techniques, various classification methods for EEG signals, which are correspond normal category, abnormal category, to understand the pattern of the EEG signal, understand the state of the human brain, understand the behavior of the human brain, assess the different nature of physiological and pathological states of the human brain. So first part in this talk, we will focus on epileptic seizure, this analysis, classification, detection. So epileptic seizures, actually these are the outcome of transient and unexpected electrical activity of the brain. So like in the human brain, there are various neurons, and then the neurons, they synchronize together and then they combine and generate high abnormal activity. Then we call it epileptic seizures. And all seizures are not epileptic seizures. When seizures, they have recurrence and they have repetition, and then this is known as epilepsy disease. So that we also call epileptic seizures. And this actually, this kind of disease affects around 2% population of the world. And we have proposed in this work the area parameter for analysis of normal and epileptic seizure EEG signals, and bandwidth parameters for classification of seizure and non-seizure EEG signals, and instantaneous area for the automated detection of epileptic seizures. Normal means these people, they never have any disease, they never had any epilepsy disease. And seizure means, epileptic seizure means that they are the patient of the epilepsy. And non-seizure means it includes seizure free and normal. Seizure free means the person's earlier he was a patient of the epilepsy, now his treatment is done, now he is actually seizure free, he doesn't have seizures. So in that way, that is known as seizure free. So these actually three methods we will see in this talk in detail. And these three methods, they are based on the empirical mode decomposition, EMD based features. And let us, before starting this EMD based methods features, let us have to understand, let us understood what is the motivation for using this EMD method for EEG signal processing. So this is actually the first technique that we use for EEG signal analysis, that was Fourier transform. And in Fourier transform, what we do, we represent signal with the help of sinusoidal functions, with the help of the periodic functions. They extend from minus infinite to plus infinite. So these sinusoidal functions, they have infinite spread, and due to that, this localization, the time localization, time concentration and focus of these basis functions, that is actually zero, because time localization or time resolution proportional to 1 upon spread in that time domain. So spread of these basis functions, that is actually infinite in time domain. So due to that, this time localization, time resolution, that actually comes out to be 0 for these basis functions. And so these basis functions are not able to represent EEG signals, because they are non-steady signals. And in order to present non-steady signal, in order to analyze non-steady signal with such kind of basis functions, they need to have time localization, they need to have the nature to handle the time varying time varying variation in the signal, time varying variation of the parameters. That is not possible with the help of these sinusoidal functions that we use in Fourier transform. So in order to apply this Fourier transform for non-steady signals, that short time Fourier transform, which we call STFT, that was proposed in the literature, and this is also called as windowed Fourier transform. So what we do in this windowed Fourier transform method, we divide a signal into different segments, and in each segment we assume that signal is stationary. and then we apply Fourier transform, and arrangement of these Fourier transform gives you analysis of non-shade signal in complete manner, so for entire signal, and that gives you short time Fourier transform, STFT. In and here like signals, whatever frequencies signal has, low or high frequencies, the window function is uniform for analyzing all kind of frequency components present in the signal. And once you have selected window, it is uniform type of the window and size of the window, and there is no thumb rule which will suggest you what should be the size and type of the window for a given signal. It is based on the trial and error method. So there is actually a need of adaptive window, need of different kind of resolution for analysis of low frequency component and high frequency component present in the signal. For low frequency component, we need actually wide analysis window. So and for high frequency component, we need a narrow analysis window. So that high frequency component needs good time resolution, and low frequency component needs good frequency resolution in order to analyze. That flexibility is not available in the window Fourier transform or short time Fourier transform. So that was the motivation for this wavelet transform. And this wavelet transform, we use actually scale function, and that is according to scale we can actually change the basis function. We say mother wavelet, and according to different scales we can have different kind of daughter wavelets, and which have different kind of resolution. So low scale gives you the basis functions which are suitable for high frequency component. They have good time resolution, and large scale provides you the basis functions which have poor time resolution, and that is actually suitable for low frequency component present in the signal. So in that way, this all frequency components present in the signal can be analyzed with the help of wavelet transform, with the help of different kind of scales, by the selection of the different kind of scales in the analysis. And this is known as multi-resolution analysis, MRA. And this wavelet transform, continuous wavelet transform, when you apply this for discrete or sample data, sample signal or this discrete time signal, and then actually it can be implemented with the help of discrete wavelets and DWT. And DWT can be implemented with the help of filter banks. So we have EG signal, for example, EG signal, then we apply to this low pass filter, high pass filter, and then we downsample by 2 each output, and that gives you the approximation detail. And again we apply this filter with the approximation detail, and then again we apply low pass filter, high pass filter, downsample by 2. So in that way actually we can get the different kind of components corresponding to different scales that we call approximation detail. So low frequency component which is known as approximation, and high frequency component is known as detail. And in that way we can perform decomposition of EG signals at various levels. But in this also, this wavelet method, there is no thumb rule which will suggest us what should be the actually the mother wavelet, what should be the mother wavelet for a given data set, and also what should be the number of levels to perform the decomposition. So that is actually that was the motivation for this empirical mode decomposition. So EMD method is actually overcomes such kind of limitations of the wavelet decomposition method. And here you don't need to select basis functions from your side. These basis functions will be extracted from the signal itself. So that is why we call it intrinsic mode functions. They are part of the signals. They are part of the signals, and by using this approach, by using this algorithm, you can use shifting algorithm, we can extract these basis functions or these intrinsic mode functions from the signals. And since they are part of the signals, so they are very useful for physiological signal analysis and classification. In case of Fourier transform, wavelet transform, we use sinusoidal functions to represent signal, or in wavelet transform we use wavelets, mother wavelet to represent signal. But your signal is not sinusoidal, your signal is not wavelet, but you are representing signal forcefully in terms of sinusoidal functions, in terms of wavelets, which are not part of the signal. But on the other hand, in EMD method, you are representing signal in terms of such functions, such basis functions, which are part of the signal. So that is whatever basic components we obtain in EMD method, they represent actually part of the signal, and that is actually so on that basis it actually justifies use of EMD kind of approach for the analysis of the signals which are highly unknown and which have a lot of variability, where it is difficult to understand the nature of the signal, and where this EMD method is an algorithm which you apply and it will extract, it will give you the components. And once you have this component, then we call them intensing mode functions, IMFs, and then actually we apply a Hilbert transform, that is a Hilbert transform, and for these components, and which will provide you analytic signal representation of IMFs. So in first method, we obtain area feature, which is based on the modified center tendency measure. And once you have this area feature, then we apply Kruskal-Weiss statistical test in order to discriminate these signals into normal and seizure EEG classes. And other method, actually this AM and FM bandwidth, we extract as a features from the IMFs, and then these bandwidth features we provide as an input to least square support vector machine classifier, which automatically classify these given EEG signal into two classes, either seizure EEG signal or non-seizure EEG signal. And the third methodology, based on this analytic IMF, we come to the instantaneous area feature, and which feature together with decision rules provide you real-time epileptic seizure detection. So these three methods we will see in the details in the coming slides. So for the study purpose, we have used EEG dataset, which is publicly available by the University of Bonn, Germany. And this dataset actually has 5 subsets, Z, O, N, F, and S. So subset Z includes EEG signals recorded under eyes open condition from the healthy subjects, and the subset O is recorded under eyes closed condition from the healthy subjects, and subset N and F, they are recorded from the seizure free subjects, and subset S includes EEG signal recorded from the seizure subjects. So each subset actually has 100 EEG signals, and that actually the each duration of each EEG signal is 23.6 seconds, and the sampling rate for these EEG signal, that is 173.61 hertz. And this data set that you can see, which includes EEG signals recorded from the healthy subjects, seizure subjects, and seizure free subjects. So this data set has the recording from the healthy subject, like normal people, patients of seizure, and patients who are treated. So this is like a very useful data for the development of the methods for the diagnosis of epilepsy. And these EEG signals which we have recorded, which have been recorded in database, they are actually based on 128 channel amplifier system. So what actually this neurologist is recorded these signals based on the visual inspection. They have categorized them into seizures, normal, seizure free, like that. So with some visual inspection, this data set has been constituted, and that this database can be used as a benchmark database, because this whatever these classes they are available in this database, which are actually they are confirmed by the neurologist. So they are already, it is known that which EEG signal belongs to what category. So we can apply our method whatever we develop, and then we can compare with these given classes, and in order to understand the effectiveness of the proposed method. So this empirical mode decomposition that we call EMD method is suitable for analysis of nonlinear non-stationary signals, and it is an adaptive method which does not require condition of stationarity of the data. So like whatever data you give to EMD method, it will give you the intensive mode functions, IMFs, whether it is a stationary signal, non-stationary signal, even it is noise. You just give some data, it will decompose automatically in the form of these IMFs. And this method is also actually data dependent method, does not require design of basis functions like wavelet in wavelet transform and sinusoidal functions in the Fourier transform. That is the beauty of the decomposition. You don't need to select any basis functions from your side. You just take the data and apply the algorithm, a shifting algorithm, and based on the residual computation, and that just it will give you the components. So this EMD method actually decomposes signal into set of narrowband intrinsic mode functions IMFs, and this narrowband components, they can be modeled using this amplitude and frequency modulated signal model, AMFM signal model, and that actually that we will use this model for the analysis purpose. And this each IMF which we derive from the EMD method satisfies two basic conditions. The number of extrema and the number of zero crossings must be the same or differ at most by 1. So this condition ensures that whatever IMF we have extracted from the signal, which is like sinusoidal function, sine or cosine function. And the second condition, the mean value of the envelopes defined by the local maxima, local minima is 0. So this condition ensures that whatever IMF we have obtained from the signal, they are symmetric in nature. So when you satisfy these two conditions, in that way, whatever components you are obtaining using EMD method, they are symmetric in nature and they look like sine cosine functions. So based on this observation, these signals actually, these basis functions or IMFs have been modeled using amplitude and frequency modulated waveform, AMFM model. So what actually we do in this method, we have a signal, then we determine maxima and minima, and then we interpolate maxima minimas, then we get the envelopes corresponding to maxima and minimas, and then we perform average of these, and that is that average mean of these two envelope, that or average value of this these two envelopes we subtract from the signal, that we call residual, and residual needs to be satisfied these two conditions. If it is not satisfying, then we repeat the process, and if it is satisfying, then we call it IMF, and then we separate it out. And next step, we subtract that particular IMF from the signal, then we repeat the same process, so we obtain second IMF. And again, for third IMF, we subtract these first two IMF from the signal, and then we determine the residual, and in that way we actually determine all possible IMFs from the signal that is actually that can be obtained by using the shifting process. So in the end of the decomposition, the signal can be represented with the help of IMFs plus residual, and these actually IMFs, they are residual is the last component from which further IMFs cannot be derived, and these IMFs are symmetric, they are narrowband in nature, they are well behaved, they are like sine cosine functions, so they are amplitude and frequency modulated waveform. So empirically, this modeling actually has been proposed. So that is why this method is also known as empirical, because this whatever based on these observations we have defined this modeling. So this is the actually example of EMD method on a signal, EEG signal, which is epileptic seizure EEG signal. And here you can see actually it has this EEG signal has spikes in the data. It has large amplitude, and that already we have seen there is synchronization of the neurons in the brain. And now how to decompose when you apply this EMD method, it will give you the different components corresponding to different scales, like IMF1, which is corresponding to large scale, that is corresponding to low scale, and high frequency, which is called as detail, and eighth IMF, that is corresponding to large scale, and which is lowest frequency component present in the signal, and which is known as approximation. So this EMD method actually can decompose this epileptic seizure signal in term from high frequency to low frequency order. This decomposition takes place. and last component is the residual. And you can see these components are well behaved, they are symmetric in nature, and they are like amplitude modulated and frequency modulated signals. And then actually it is very useful set of features, set of components or basis functions which can be used further to define the features. So in the proposed method, actually is based on the analytic signal representation of IMFs. So we have used Hilbert transform, and we have IMF plus J times its Hilbert transform, which gives you analytic IMF. And this analytic IMF says this is a complex signal, and it has time varying amplitude and time varying phase. And derivative of time varying phase gives you instantaneous frequency. So this analytic signal representation for each IMF, we can have a model like in equation 2, that is like a time varying phasor, and where this AMT represents the time varying amplitude of the mth IMF, and phi mt represents the time varying phase for the mth IMF. And this mathematical representation or analytic signal representation of IMF is very useful because it satisfies two interesting conditions. So the first condition, the plot has direction of rotation, and the rotation in the plot has unique center. That is beauty of this analytic signal representation. That if you apply analytic signal representation on a signal itself, then you will not see these two conditions. So that shows the application of EMD method when you apply this method, and when you see the analytic signal representation of the components, then you have this kind of interesting conditions. So based on these two conditions, we have defined this very interesting parameter that is we call area parameter. And here you can see the analytic signal representation of EG signal, and there is absence of the any geometrical symmetry, any like circular pattern. It has multiple centers, so there is no specific geometry. On the other hand, if you see analytic signal representation of various components, various IMFs, IMF1, IMF2, IMF3, IMF4, there we have nice circular structure. And this circular structure has unique center 0, 0, and it has unique direction of rotation, which actually help us to define area parameter. That is the motivation for actually defining this area due to circular symmetry. It actually motivates us to define area parameter for the discrimination between normal and seizure EG signals. And when you see this analytic signal representation pattern for normal class and abnormal class seizure class, then during this seizure classes, seizure EG signals, there is actually this area parameter is increased. So this that is very interesting phenomena, and that actually we have explored for the classification without using any machine learning method, based on the analysis itself for the normal and seizure classes. So how to determine this area parameter in an automated manner? So for that we have proposed modified center tendency measure, that is CTM. And if we have n number of total number of points in the data, and suppose R is the radius of the central area, then modified CTM is actually defined by the equation 3. And in this expression, delta dn is 1 when this point which we actually if it is falling inside the radius, otherwise it is 0. So CTM tells us for a given radius how many points are falling in the inside the radius and how many are outside the radius. So that is actually, so for example, if CTM is 95%, this means out of total points, 95% points are the 95% point data samples are under the selected radius. So in this study, we have used 95% CTM as a feature or as a criteria to determine the radius. And once you have radius of the circular pattern, then we compute the area from that radius, and which has been studied for the analysis of normal and seizure classes of EG signal. And after that, we have computed instantaneous area parameter which is based on this area from the area of the different segments of the EEG signal. So we have intrinsic mode functions IMFs, and we divide this IMF into different segments, and then we compute the area for each segment, and then we interpolate that these different areas values, and that gives you instantaneous area. And the instantaneous area actually has been computed by using moving window method, and the selected size of each moving window is 3840 samples, and this window size is uniform for all EEG signals. And instantaneous area of mth IMF is defined by the equation 4. So here actually you can nicely define the instantaneous area based on the instantaneous radius. And then in other part, actually we have used amplitude modulation and frequency modulation bandwidth of analytic IMFs for the classification of the seizure and non-seizure EEG signals. So generally, when we talk about the bandwidth of the signal, we always think about the Fourier transform. So for a signal, we apply Fourier transform and we go in the frequency domain, and we see the spread of the signal in frequency domain. So Cohen and Lee, they in 1990, they come up with the criteria or definition of the bandwidth, which depends on the amplitude modulation and frequency modulation components of the signal. And this actually, like equation 5 gives these equations, the equations for computing this bandwidth due to amplitude modulation and bandwidth due to frequency modulation. But how to get AM/FM component, mono-component AM/FM signal in real life? It is very difficult to get mono-component AM/FM signal. And this empirical mode decomposition EMD provides such a platform where nicely you can decompose this multi-component AM/FM signal in terms of mono-component AM/FM signals, and this bandwidth parameters can be computed. So this bandwidth due to amplitude modulation, bandwidth due to frequency modulation can be obtained. So now we will see some experimental results or simulation study. So the first part, analysis of normal and seizure EEG signals. So subset Z from the normal class and subset S from the seizure class. And in this method, actually we can detect patients with epilepsy using EEG signals from normal people. And the EMD based decomposition help us to cover more than 95% of the data points which lie within the circle due to having circular form of the analytic IMFs. And the area parameters have been estimated for both the classes, normal and seizure, based on the analytic signal representation of IMFs of various window sizes. For example, 500 samples, 1000 samples, 2000 samples, and 4000 samples. And this plot actually shows the CTM in terms of percentage, the versus radius plot. And here you can see, like for normal class, the requirement of radius is around 300 in order to cover 100% CTM. And for the seizure class, the requirement of radius is 1200 in order to have 100% CTM. So this actually figure shows that the requirement of radius is less as compared to the requirement of radius for normal class is less as compared to the requirement of radius for seizure class. So accordingly, this area parameter will be also less for the normal class, and it will be higher for the seizure class. And then we have studied this comparison between normal and seizure EEG signals based on the Kruskal-Weiss statistical test, and for the window length of 4000 samples for the first 4 IMFs, IMF1, IMF2, IMF3, IMF4. And here you can see we get the probability value for this analysis, that is 0. So that is if probability value is coming out to be less than 0.05, then we call it a statistically significant difference between these two classes. And in this study, the probability value is coming out to be 0. So that shows the statistically significant difference between this normal and seizure classes of EEG signal. And after that, we have compared the seizure and non-seizure and normal classes of EEG signal using this area parameter for window length of 2048 samples. And in this case also we get probability values equal to 0. So that also shows the statistically significant difference between these two classes. And then we have computed area parameter based on this Kruskal statistical test for normal and epileptic seizure classes based on the window size of 2000 samples for the first 4 IMFs, and here we also get probability value equals to 0. So which shows the statistically significant difference between these two classes. And after that we have studied this discrimination between normal and seizure classes of EEG signals for the window length of 1000 samples, and in this case also probability value is coming out to be 0. So that shows a statistically significant difference between these two classes. And same is true for 500 samples also. Here also probability values are 0 for these first 4 IMFs, and so shows the statistically significant difference between that. And it is also clear from the box plots for this normal and seizure classes. So same thing, whatever we have seen in the form of box plots, we can see in the form of table. So in this table, this for the normal and seizure subjects, the different window sizes, 500, 1000, 2000, 4000 samples, and you can see the area value, minimum and median and maximum value of the area parameter for IMF1, IMF2, IMF3, IMF4. And nicely, these area parameters, they are able to separate these classes, normal and seizure. And this, in case of seizure, this area parameter is larger as compared to the normal classes. And this, then we have compared this proposed method with other existing methods in the literature. So like Nigam and others 2004, Srinivasan and others 2005, Kanatharal and others 2005, Polach and others 2006, Suvasi in year 2007. They have used various signal processing machine learning methods in order to develop this intelligent computing system, to detect this normal and seizure EEG signals. And they have got actually various classification accuracies that you can see this table. And the proposed method can detect this seizure and without applying any machine learning algorithm. So that analysis technique itself is sufficient so that you can get such a nice feature which can provide better discrimination between normal and seizure EEG signals with 100% accuracy. And here actually we don't need to use any machine learning method, because already based on the simple threshold, these two classes can be separated. And the selection of the spoon depends on the type of food, and if you want to have noodles, then we use fork. So similarly here, according to signals, we have got such a set of basis functions, such kind of analysis technique, that EMD, which is perfectly suitable for the signal analysis, so that there is no need of classification. Already analysis itself is sufficient to perform the classification. And after that, we have actually performed the classification of seizure and non-seizure EEG signals. So in this study, the subsets Z, O, N, and F, they are combined to form the non-seizure class, and subset S form the seizure class. And this methodology can detect patients which have epilepsy from the normal and seizure-free people or non-seizure people. And the EMD method decomposes the nonlinear non-seizure signal into a set of narrowband FM components or IMFs, and then we actually compute bandwidth parameter, bandwidth due to amplitude modulation and bandwidth due to frequency modulation. And these bandwidth features help us to find the contribution due to amplitude modulation and frequency modulation in the signal. So these are the results that for the bandwidth due to amplitude modulation based on the Kurzgesagt statistical test. The first part, in the first figure, you can see the results for first 4 IMFs, and the second figure you can see the results for the remaining IMF, 5th to 8th IMF. And this first figure, this actually bandwidth due to amplitude modulation feature is able to separate the seizure and non-seizure classes, and but it's not perfect separation. And on the other hand, if you see IMF 5 to 8, these IM bandwidth feature due to amplitude modulation is not able to separate these classes, two classes of EEG signal. Same is true also for bandwidth due to frequency modulation. And here you can see the first figure, this first 4 IMFs, this bandwidth due to frequency modulation feature is able to separate the classes. But this is not true for the remaining IMFs, like IMF 5 to 8. Here this bandwidth due to frequency modulation feature is not able to separate the classes, and that actually that we have also studied the probability value based on the cross-curve statistical test. And the first feature bandwidth due to amplitude modulation frequency modulation, the first four IMFs, the probability value is coming out to be less than 0.05. So that is statistically significant difference. And the remaining four IMFs, they are not able to show the difference between these two classes. So based on these probability values, we have actually selected the first four IMFs and corresponding these features. And then we have seen, like earlier case, area parameter was able to separate these classes normal and seizure. Here this separation is not perfect, it's not 100%. So we need to go in such a domain where these features can be separated. So that motivates us to use least squares support vector machine classifier in order to obtain more accurate classification. So the effectiveness of these bandwidth features, this bandwidth due to amplitude modulation, bandwidth due to frequency modulation, for the classification of seizure and non-seizure signals, we have actually used LSSM classifier. And for two-class support vector machine, we consider the following decision function, which is shown by the equation 6, fx equal to sine wt gx plus b. And here w is the L-dimensional weight vector, and gx is the mapping function, and b is the bias. And based on this decision function, we can determine whether based on the sign like a binary classification can be done. That if it is plus, then we can say seizure, and if it is sign is minus, then we call it non-seizure. So this is just a simple block diagram of the LSSM classifier. We have actually extracted the features from the data or these signals, and then we take some set of feature that we call training set, and with the help of this kernel function and its parameters, we actually perform the training of the LSSM classifier. So we generate the actually nice feature space, where we use testing set to perform the classification, and that is based on the decision model fx equal to sine wt gx plus b. And if based on a sign, if the output is 1, then we call it one class, and if the output is -1, then we call it another class. So in that way, binary classification can be performed. And in this study, the following kernel functions have been used: like polynomial kernel, which is defined by the equation 7, and radial basis function, mathematically defined by the equation 8, and Mexican head wavelet kernel function, which is defined mathematically by equation 9, and Morlet wavelet kernel function, which is defined by the equation 10. And the three classification performance measures have been used. This is the like sensitivity, specificity, and accuracy. Sensitivity is the proportion of the epileptic seizures which are correctly detected by the algorithm, and specificity is the proportion of segments without seizures and which is correctly identified by the algorithm, and accuracy is the proportion of correctly detected seizures and non-seizures by the algorithm. And mathematical expressions for these three measures you can see in the slide. And here TP is the true positive, and Fn is the false negative, and Tn is the true negative, and Fp is the false positive. So in that way, these three classification performance measures have been computed, and this table shows the sensitivity, specificity, and accuracy, like these performance measures of the first four IMFs with different kernels of the LSSM classifier for classification between non-seizure and seizure EG signals. In this kernel function, polynomial RBF, Mexican head, and Morlet, and this kernel parameters have been computed based on the trial and error method. And then we have statistical parameters, sensitivity, specificity, accuracy, and then these are the first four IMF. These are the values of these performance measures, minimum to maximum. And you can see this Morlet wavelet kernel function is for the second IMF is able to provide the best performance in all other kernel functions and IMFs. And this also validated with the help of this receiver operating characteristics curve, ROC curve, and this area under ROC curve is also another parameter which is also used to measure the performance of the classifier. And here we have also computed area under ROC curve for different kernels, polynomial, RBF, Mexican head, and Morlet. And you can see this Morlet kernel function provides area under curve equals to 1. So that actually that gives you the better performance with respect to other studied kernel functions. So this earlier also this whatever like sensitivity, specificity, accuracy, these three performance measures, they were also higher for the Morlet wavelet kernel function, and this area under ROC curve, which is also higher for this Morlet wavelet kernel function. So this validates that like this Morlet wavelet kernel function provides better classification performance for the classification of seizure and non-seizure classes using EEG signals. And this is very interesting actually plot which can be used for the automated diagnosis of epilepsy in the rural areas, especially like and this is also known as computer-aided medical diagnosis or computer-assisted medical diagnosis, intelligent systems, intelligent computing, expert systems to perform the diagnosis of epilepsy. So this is based on the after training we have feature space, and that during testing phase it shows the well separation of the classes, seizure and non-seizure classes. So what actually we do for a given EEG signal, we apply this empirical mode decomposition method. Then it will separate into various IMFs, and you will get various IMF. Then we select second IMF from the signal, and for the second IMF we determine this bandwidth features, bandwidth due to amplitude modulation, bandwidth due to frequency modulation, and then we map these features in the feature space. And if it is coming in the shaded area, then we call it a seizure, otherwise it's non-seizure. So based on this mapping, based on the region where this feature is located, we can separate out, we can make the decision whether this person is having epilepsy or not. And this such kind of actually tools, such kind of decision systems are in the form of software which can be used in the smartphones, mobiles, laptops, computers, which these days nearly many people are using, you know. And this is so in that way smartphone will become really smart, and because it is always assessing the disease, and if you have this epilepsy disease, so in the initial level it can be detected, and it can be informed you, warning can be given, then you can go to hospital and required treatment can be taken. So we have also actually compared this method with other existing methods in the literature for classification of seizure and non-seizure EEG signals. So Stadla 2007, Okak 2008, Yang 2010, Lingen 2011. They have used various signal processing machine learning methods to design these intelligent systems, intelligent computing systems, where they have achieved various accuracies that you can see in this table. And the proposed method that is actually based on the empirical mode decomposition, bandwidth features, and least square support vector machine classifier provides that accuracy between 99.5 to 100. And so that actually gives you better performance than other existing methods in the literature. And after that, we have also done work on epileptic seizure detection. So this detection of epileptic seizure based on the visual inspection of EEG signal is very time consuming, and that we have already seen it may be inaccurate also, especially for long data recordings. And suppose somebody is driving a car and he or she is going to have epilepsy attack, then such methods can detect in the initial level. They can detect and they can generate the warning, and that alarm actually help us to the person to take the epilepsy drugs, and based on that, once he or she has taken epilepsy drug, then this attack can be bypassed. So it is very useful actually techniques or useful actually for the epileptic patients. Such kind of devices or detection systems, they find actually a lot of applications for the epileptic patients. And when a seizure occurs, these automated seizure detection systems can help in providing immediate required treatment for the epileptic patients. And for this work, we have used instantaneous area parameter, which is measured from the IMFs, analytic IMFs of EEG signals, and that provides rule-based detection of epileptic seizures. And the EEG dataset, which is publicly available by the University of Freiburg, Germany, has been used in this work. And this data set includes invasive EEG recording of 21 patients which are suffering from medically intractable focal epilepsy. So there are two types of EEG recording. One is recorded from the surface of the brain, that is known as surface recording, that is non-invasive, and other one is actually invasive EEG recording. So they are recorded from the inside of the brain and it requires some surgery. And this, when you have generalized epilepsy, then this surface EEG recordings are sufficient for diagnosis. But when you have focal epilepsy, then a particular region of the brain actually is affected by the seizure, and that is actually fixed. So in order to identify that region, there is a lot of role of the signal processing, lot of role of EEG signals, which we record from the inside of the brain. That is invasive EEG. It requires surgery. And based on the signal processing machine learning methods, which actually can be developed intelligent computing system, which can detect this area automatically, and we can perform the surgery. We can remove that area. So in order to perform diagnosis of focal epilepsy. So this EEG database, which have been acquired here in this database using digital video EEG system with 128 channels, and its sampling rate is about 256 hertz, and 16 bits analog digital converter has been used. And in this study, 3 intra-source records of 9 patients with focal epilepsy, which is originated in the temporal lobe region, have been selected. So total 90 segments we have per channel, and 51 of them seizure free, and 39 segments are having only one epileptic seizure. So this is actually very interesting plot, interesting signal and its IMFs, and you can see the signal first sub figure, and signal has actually got epileptic episode, that is in the middle of the signal. And when you decompose this in terms of IMF, first 3 IMFs, then you have nice boost up regions. This episode is more clear in the decomposed IMFs. Then we have actually determined instantaneous area of these IMFs that you can see in the figure. And these circles, they are shown in the beginning and ending. They are onset, offset of this epileptic seizure. They are by the proposed method, detected by the proposed method, and these lines, dashed line in beginning and ending of this episode, they are actually obtained by the neurologist or by the doctors. So we have used these boundaries as a reference in the beginning and ending of this epileptic episode. And you can see whatever we have detected, the beginning and ending of this episode, that is also in the range of the defined by the neurologist. And here also actually you can see this seizure is becoming very severe in the middle, but by doing this the feature, we can detect in the beginning itself. So that gives you the nice actually detection of the seizure sufficient time before, so that you can perform diagnosis or whatever activities you are doing. You are driving car, you can stop it and you can take the required medicine. So that is that time can be used to bypass that attack. So for this, for developing this method, we have actually proposed 3 decision rules. So the first decision rule requires the computation of threshold of instantaneous area for the IMFs of each signals for all channels, and the threshold of mth IMF is computed by equation 11 in empirical manner based on a trial and error. And the second decision rule requires the identification of those seizure activities which are available in at least 2 of the 3 instantaneous areas of IMF for each channel. And third rule requires making an interchannel decision based on the identification of the seizure activities which are available in at least 2 of the 3 channels, where presence of seizure activity in each channel decided by the rule 2. So in that way, these are actually 3 rules that are used, and we take decision in the favor of the channels. Out of 3 channels, if 2 channels are in the favor of epileptic seizure, then we call it seizure activity. If out of 3 channels, if 2 channels are in the favor of seizure free, then we call it seizure free activity. So this table shows the performance evaluation parameters for the proposed method. So for the different patients, we have number of segments, then we have true positive, true negative, false positive, false negative, Then we have sensitivity, specificity. Already it is have been defined in the earlier slides. And this PPV and positive predictive value, negative predictive value, and error rate detection. These performance measures that are defined in the below of the slide, in the bottom of the slide. And this PPV, NPV, SEN, sensory specificity, PPV, NPV, these parameters are expected to be high. And you can notice that these parameters in our proposed method, they are coming out to be high. And on the other hand, ERD is expected to be less, and it is coming out to be less also. So this method, whatever we have proposed, it is providing us performance as per our requirement. So that is actually is giving like performance in right direction. And after that, we have compared this proposed method with other existing methods in the literature. Orozco and others in 2009, and Correa others in 2009, they used this energy of based parameter, energy based method, energy of the signals, energy of the IMFs, and they got various parameters, sensitivity, PPV, NPV, ERD, that you can see in the table. And the proposed method actually provides sensitivity, specificity, positive predictive and negative predictive ERD, error rate detection. That is actually better than the other existing methods in the literature. So the sensitivity, specificity, PPV, NPV is better, higher, and ERD is lesser as compared to the existing methods. So our proposed method actually provides the better detection performance of epileptic seizure EEG signals as compared to the other existing methods in the literature. And after that, we have proposed time frequency image based features for classification of sleep stages. That is actually very interesting domain these days, and these days a lot of actually work people are using time frequency domain, time frequency image, where this one dimensional signal can be converted into time frequency image. And we can use convolutional neural network, this advanced machine learning technique, that deep neural network based on the images. So this whatever work in this this part, we will see that also can be used as a platform where this one dimensional signal can be converted into two-dimensional images, two-dimensional signal, which we call images, and nicely advanced machine learning techniques like convolutional neural network, deep neural networks can be used to develop the intelligent computing systems for the classification of various physiological signals. So these EEG signals are commonly used for the classification of sleep stages, and there are multiple, actually this is multiple classification problem, and very useful for the diagnosis of sleep disorders. And the standard method for the sleep staging that is actually proposed by the RNK standard in 1965, around 1965. And according to RNK standard, this entire sleep pattern can be classified into 6 sleep stages. So first one is awake, and second one is non-rapid eye movement S1, S2, S3, S4, and last one is rapid eye movement REM. So total 6 sleep stages are there, and the rapid eye movement, that is actually is very useful stage. And if you see alcoholic people, they cannot have this stage. So alcoholic people actually, they are not completing 6 stages, they complete only 5. So that is indirectly they are accumulating the sleep related disorders. And this rapid eye movement that is in India actually that is very deep sleeping, and we call it Brahma Murta, morning time around 3 to 5 o'clock. And this stage actually is like responsible for the dreams, deep sleeping, and it makes like lot of sense sometime when you see the dreams in this. So a lot of research is going on this stage of the sleep to understand the dreams. And if you go to a very old time like Ramayana time in Treta Yoga, Mandodari actually predict in the dreams she has seen this Ravana is going to die, and that is based on the actually in the dreams she predicted. And she also mentioned this Shuravar that she has seen in the dream that you are going to die. And so this sometimes this information from the dreams is going to be also used to understand the actually in old time people used to use this information for understanding this this actually understanding the future or predicting the future. And if even rural areas also, if you see sometimes when you see the dreams, then if you inform, if you tell to your friends or like some persons in the neighbors in the village or your family member that you have seen the dream, then they will ask you what time you have seen the dream. So if you say that I have seen in the dream in the around 12 o'clock in the night, then they will not take it seriously. But if you say I've seen dream in the morning time, then they will take it seriously. So based on the different like objects or different actually things you see in the dream, there is a lot of predictions people predict. And for example, rural areas, some girl has seen the bangles in the dream. Then people actually rural areas they predict that she is going to get married this year. And there is a lot of celebrations, and this is then in that way they predict that this work is going to happen. So this is actually in especially rural areas, people do a lot of actually, or automatically they use a lot of computing system, lot of predictions, lot of intelligent systems, but in different way. So life is more stochastic, more actually more uncertain in rural areas as compared to urban areas, and there people use in the whatever research we do in different ways. And recently, this American Academy of Sleep Medicine (ASM) that actually they has combined sleep stage S3 and S4 of RNK standard. So according to that American Academy of Sleep Medicine, now instead of 6 sleep stages, we have 5 sleep stages. So now, according to RNK standard, the sleep stage pattern can be represented by 6 sleep stages, and according to American Academy of Sleep Medicine, this pattern is represented by the 5 sleep stages. So now, how to classify these stages, and there is a lot of actually motivation for developing methods which are based on the signal processing machine learning techniques to develop automated systems which can define, which can identify these stages in an intelligent manner. So we have proposed this method which is based on the smooth pseudo-Vignaville distribution and a least square support vector machine based classification, intelligent computing system, which can be used to determine the various sleep stages using EEG signals. So we have EEG signals of different sleep stages, then we apply time frequency representation based on the smooth pseudo-Vignaville distribution method, and then based on this time frequency representation computed, and then it is converted into time frequency image, and where these frequency bands of the rhythms they are used to segment the time frequency image. And then we have segmented time frequency image corresponding to these frequency bands are used for the determine the features based on the histogram of sub images of the EEG signal, and then these features are given as an input to multi-class least square support vector machine classifier, which give you the classification of 6 stages according to RNK standard, and the classification of 5 stages according to American Academy of Sleep Medicine. So this EEG data set in this work actually for sleep stages that we have used publicly available database, which is available at the PhysioNet website, PhysioNet, and these recordings have been obtained from the 8 males and females subjects whose age vary from 21 to 35 years. And the recording includes horizontal, this PZ, CZ, PZ, EEG signals, and each sample at 100 Hz. So according to RNK standard, this EEG database actually have been developed, and these signals are recorded for 5 hours, like 12 o'clock in the night to 5 o'clock in the morning. So this 5 hours time is sufficient to record these different sleep stages, which will include all the 6 sleep stages. And then we have computed a smooth pseudo-Vignaville distribution method. Actually, this is defined by equation 11, and you can see the computed smooth pseudo-Vignaville distribution in the figure that. And then this is converted for a EEG signal, and this is converted into time frequency image. So this is the gray image representation of time frequency image based on the smooth pseudo-Vignaville distribution of rapid eye movement sleep stage of EEG signal. And then we have actually we have obtained gray and binary sub images representation of time frequency image corresponding to frequency bands of delta rhythm, theta rhythm, alpha rhythm, beta rhythm, and gamma rhythm. And then we have actually determined the histogram of gray and binary subimages of time frequency image corresponding to frequency bands of beta rhythm, theta rhythm, alpha rhythm, beta and gamma rhythms. And then we have obtained these features which are based on the histogram of subimages of the EEG signals. So this maximum count of pixel intensity histogram is obtained by equation 12, and the spread in the histogram of gray subimages is obtained by the equation 13, and the aspect ratio in the histogram of binary subimages defined by the equation 14. And then once you have these features, then like earlier you have seen this least square support vector machine that was actually applied for binary classification. But here now classification problem is multi-class classification problem. So we have used multi-class least square support vector machine in order to classify these multiple stages, multiple sleep stages using EEG signals. So the decision function of multi-class least square support vector machine is defined by the equation 15. So here kernel function, like earlier it was one kernel was required, but here since it's the multiple classification problem, so you need to define multiple kernel function. So the following kernel functions have been used, like radial basis function for the kth class is defined by the equation 60, and Mexican head wavelet kernel function which is defined by the equation 70, and Morlet wavelet kernel function is defined by the equation 18. Now after that, actually what is the reason for the segmentation and why we need segmentation? So what we have done, we have also studied this without segmentation time frequency image and with segmentation of time frequency image, this classification problem, multiple classification problem. And we have used the same kernel function with the selected parameter based on a Taylor method. And we have observed that when you perform the classification with segmentation of time frequency image, then we get better performance as compared to the without segmentation of time frequency image. So for example, like if you use Morlet wavelet kernel function, and then without segmentation time frequency image, we get 79.99% total accuracy. On the other hand, you perform segmentation of time frequency image, then we get 92.93%. So there is huge improvement in the classification performance, which motivated us to go for the segmentation of time frequency image before classification process. So these results are corresponding to window size of 64 samples of EEG signal. And this table shows the confusion matrix for the classification accuracy of the sleep stages of EEG signals for Morlet wavelet kernel with window size of 64 samples. And then we have compared our method with other existing methods in the literature. So according to RNK standard, and here you can Dorosenkov and others 2007, Burale 2010, they use various signal processing machine learning based method, and they got various accuracies for different sleep state detection that you can see in the table, and total accuracy also has been shown for different methods. And the proposed method actually that is based on the time frequency image based features and multi-class least square support vector machine classifier, which provides better classification accuracy for the individual stages as well as total accuracy also. So this means our proposed method has provided better performance as compared to the other existing methods in the literature for RNK standard. And American Academy of Sleep Medicine standard, there is very less work has been done. And here you can see this Su and Ras 2013, they use energy-based features and lemon neural classifier, and they got different. You can see the awake S1, S2, S3, S4, RAM total accuracy in terms of percentage. And proposed method has provided better than Su's method, which uses time frequency image based features and multi-class square support vector machine classifier. And you can see that there is huge improvement in the classification performance as compared to the Su methods in 2013. So our proposed method has provided better performance as compared to the other existing method, which is studied on American Academy of Sleep Medicine database. And after that, this multi-wavelet transfer-based features for human emotion classification have been suggested. And these EEG signals actually include very useful information related to different emotional states, and which help us to understand physiology and psychology of the human brain. So if you have any problem related to anxiety, depression, stress, and if you go to doctor, they will ask you for EEG signal. So this EEG signal is very useful actually technique to understand the psychology and physiology of the human brain. And there are various other methods also to understand the emotions. There will be like a speech processing based method, face recognition based method. But these methods, they may be mislead. They can be manipulated because face can be modified, and your speech signal can be intentionally they can be changed. On the other hand, these EEG signals, they are recorded from the inside of the brain. They represent the electrical activity of brain, and it is very difficult to influence electrical brain activity intentionally. So due to that reason, we have actually used EEG signals for the study of human emotions, and the emotion classification based on EEG signals can help us to develop improved brain computer interface system, BCI system. So sometimes we have people they are not able to speak, and for them we can have EEG signal as a tool, as a means to interact with the real world. So for example, suppose the person is not able to speak, or newborn child, he is not able to tell what he is feeling, he is not well. So the medicines actually tell this treatment can be performed, and we can record the EEG signal after treatment. And based on the signals, EEG signals, such kind of actually intelligent computing system can tell us, for example, happy emotion. So then this person actually is showing effect of the treatment. So this person is feeling well. So this newborn child is feeling well. So based on the EEG signals, if you determine the emotion, then we will understand what is going on. That is actually useful for the people, they are physically disabled and impaired people, and they are not able to interact with the real world. So this EEG signal based BCI system, which is also developed based on signal processing machine learning algorithm, which provides us an intelligent computing platform where nicely we can compute the state of the human brain, and it's, for example, is not good and not bad. So these, based on this such kind of actually automated emotion detection, these days many applications are coming, like in the car, that during driver people want to listen various songs. So according to your emotion, songs will be played. Suppose you are happy, then happy songs will be played. If you are sad, then sad songs will be played. And even you are coming to your home from the work, then you, based on these methods, your family will come to know which kind of emotion you have today. Accordingly, they will behave with you. So this is such actually are very useful techniques to understand the human behavior. So that is based on the emotion. That is the difference between animals and men. The human and animals, if we don't have emotions, and then like animals. So so that is why emotion makes us different than the animals, and such actually BCI systems are able to detect emotions even you are physically disabled or impaired people. So this is the proposed method, block diagram of the proposed method. We have experiment set up, then we record the signals. The signals sometimes they are contaminated with the noise, they have artifacts, they are not well recorded. So then we need pre-processing to get the well-behaved signals. Then we apply multi-wavelet transform, and which gives you the EEG signal from different subbands. Then we apply Euclidean distance based features from three-dimensional phase space reconstruction, and then these features are given as input to multi-class G-square support vector machine classifier, and which will automatically classify happy, neutral, sadness, and fear emotions. So these EEG signals have been collected from 8 healthy subjects, 4 males and 4 females, whose age vary from 20 to 35 years during audio video stimulus. In the literature, if you go, and many studies, they only studied actually female subjects for the human emotions. And it has been shown in the literature, they are more sensitive for emotions for the female subjects. And sometimes they people have studied both males and females, and for females also it is up to some age. After that age also they are like males in terms of emotions. So in this study we have actually studied both kind of subjects, these males and females, for the human emotion assessment. And these subjects were the undergraduate students or employees from IIT Indore, And the 16 channel EEG module is a biopac system in compliance to the international 10 to 20 system has been used for the recording of EEG signals. And the sampling rate of 1000 hertz of the EEG signals with bipolar montage for this study has been selected. So this study has examined 4 emotional states, which includes happy, neutral, sadness, and fear emotions, and 3 audio-video stimulus with 5 trials for each emotion from 8 subjects with 3 F4 channel of E signal have been used, and total 480 signals have been actually studied with 2-second duration. And these figures shows the electrode cap, where location of the electrodes which we have used for the recording of the signals. And this also shows the arousal and valence block diagram where these emotions are located. So this is the complete actually block diagram of the proposed methodology. We have video, audio, many people they listen music. So there may be various inputs in terms of audio, video, music, and they can be used to introduce the emotions. So once these emotions are introduced, then we can use the EEG recording system to record the EEG signal for different emotions. And then we have EEG data, then we perform pre-processing, and then after that we have well-behaved EEG signal, then we apply non-state signal decomposition methods, then it will give you features, and then we apply multi-class least square support vector machine classifier in order to classify these emotions. So this multi-wavelet transform is an extension of the scalar wavelet where multiple scaling functions and multiple mother wavelets are used instead of single scaling function or single mother wavelet. And the multi-wavelet actually offers the various advantages like simultaneously exhibit orthogonality, short support, symmetry, and second order approximation. And in this work, we have used 3 commonly used multi-wavelets, GHM, CL, and SA4. And after that, once you have this multi-wavelet decomposition, then you have subbands. And then subbands, they have actually non-linear dynamics. So in order to extract non-linear dynamics of these subband signals, which we obtain from multi-wavelet decomposition, we have used phase space reconstruction concept. And the mathematical expression for phase space reconstruction of subband signals are expressed by the that is this mathematical expression shown in the slide. So this example shows the third level subsignals. So when you apply this to compute third level, then you will have 4 subbands. One is one approximation, 3 details. Then for each subband signal, we have obtained phase space reconstruction plot, and that. So now how to quantify the nonlinear dynamics, which is actually available in this 3-dimensional phase space representation, or 3-dimensional phase space reconstruction. So that that is actually mean of Euclidean distance and standard deviation of Euclidean distance that have been proposed by us to quantify this variability present the subband signals, and that is based on the 3-dimensional PSR. And one can study higher dimensional PSR also, and for this work or other applications. And this Euclidean distance, that is always actually single one-dimensional signal. This is the beauty of this method. So even if you go to 3-dimensional PSR, then you will have one-dimensional signal. Then you can extract these features. If you go 4-dimensional PSR, then also you will have one-dimensional Euclidean distance signal. Then you can extract features. So you can study various dimensions of this phase space reconstruction, and that is very easy to compute. And then you can determine one-dimensional signal from that higher dimension, and you can extract various features. So it will give you another kind of domain where you can develop methods. So now we'll see some experimental results. So in the proposed method, GHM, CL, and SA4 multi-wavelets have been employed for obtaining third level decomposition. So we have 4 subsignals, 4 subband signals for each EEG signal, and then we compute phase space reconstruction of the each subsignal in order to obtain the more meaningful representation for nonlinear data, nonlinear subband signals. Then we have used mean and standard deviation of Euclidean distances of 3D PSR in order to quantify the complexity, nonlinearity of these decomposed subsignals, which is linked with the different emotional states of the brain. And then these features, whatever we have computed, we have given as an input to multi-class support vector machine classifier. with RBF kernel, Mexican and multi-wavelet kernel functions. So this table shows the various multi-wavelettes used, GHM, SA for SEL, and kernel function parameters based on parameters which are selected with the trial and error method, and various emotions, happy, neutral, sad, and fear, with different accuracy can be actually obtained. And you can see from this table, this CL multi-wavelet together with modulate kernel function provides actually total accuracy of 91.04%, and that is actually higher than the other methods, other kernel functions and other multi-wavelets. So this is the confusion matrix of the modulate wavelet kernel function of the multi-class histogram support vector machine classifier for the classical human emotions using EG signals with CL multi-wavelet. And then we have compared this proposed method with other existing methods in the literature by Lin and Bian and others. And here you can see this other method, they use music, video, and we have used audio, video, stimulus, and different channels are there. And our proposed method also require very less number of channels. And the accuracy that we have achieved, which is higher than the other existing methods, and we have studied the same classes of EEG signals for the emotion identification. So this is the conclusion of this entire talk. Area which we have measured from the complex plane or analytic IMFs, which have circular pattern and which is very useful for separating the normal and seizure classes of EEG signals. And that is very good actually. This area parameter is simple parameter which can be understood by the common person. For the disease, everyone is same, whether you are professor, you are a student, you are farmer, you are labor, or you are contractor, you are engineer, doctor, whatever. For the disease, you are the same. It can go to anyone. So the parameters should be like that it can be understood by the common people. So we believe that this area parameter is such a simple parameter which can be visualized by anyone, which can be used by anyone to assess the disease due to epilepsy disorder. Bandwidth parameters, bandwidth due to amplitude modulation, bandwidth due to frequency modulation of the IMFs of EEG signals are very useful for developing intelligent computing system in order to classify seizure and non-seizure EEG signals. And we have seen this modulate wavelet kernel function of LSSVM classifier provides very good classification accuracy for the automated classification of seizure and non-seizure EEG signals. And we have proposed patient-specific system for the automated detection of epileptic seizures using EEG signals. And the instantaneous area can determine this epileptic seizure at any point of time. That is the beauty of the method. And this is rule-based detection, so it is more reliable as compared to the bunch channel. So it is based on 3-channel, and that is more reliable. We can take the decision in the favor of the majority. Time frequency image representation, which is actually very useful concept, and these days there is a lot of interest in the literature to apply this advanced machine learning algorithm like CNN or deep neural network in the data in the form of image. And this method can convert this one-dimensional data like signals in the form of image, and where you can nicely apply this advanced machine learning methods. And we have seen this time frequency image representation of these signals when you decompose in the terms of frequency bands. Then based on the histogram features, we can classify the different sleep stages according to RNK standard, according to American Academy of Sleep Medicine, with very good classification accuracy. And last method, mean and standard deviation of equivalent distances, which are based on the 3-dimensional phase space reconstruction of subsignal which we have obtained from the multi-wavelet transform, can be used to detect various 4 classes of human emotions based on the EEG signals. And based on the CL multi-wavelet, actually we have got very good classification accuracy for the automated classification of human emotions. And these all actually, these methods, they are nicely, they can be considered as intelligent computing system. Where you just give the data and input signals, and without presence of human, without actually human involvement, automatically it will tell you whether this person is belong to this class or this class, normal, abnormal. And so such kind of systems They're very useful for the diagnosis of diseases and based on the EG signals, and that is actually very good for healthcare. So thank you very much.
Yes, thank you, sir. Yes, any questions from the participant side? Yes, ma'am. Yes, ma'am. Yours is audible. Any questions from the participant side? Sir with us? Anyone? Yes, can we are just waiting, sir. Some questions is there. I think no questions from my audience side, sir. Okay, sir. Thank you, sir, for giving this lecture for our participants, sir. This is very informative for us and for the participants. And the most of the things sir is covered related to the brain signaling and how you decompose the signals. So this all you can use in your future projects and the learning point of view. You can contact further to sir also. Sir, could you share your email ID here, sir?
Yeah, yeah.
Jaya Bean from Jaya Bean. Any questions from your side? Swapna? Because sir, with us you can ask. Sir, some of the students are saying kindly share your PPTs.
Yeah, I will do that. I will share PPT.
Okay, sir. So you will send to my email ID. I will share to all. Okay, sir. Thank you for nice session, and we enjoyed a lot for our session. And we are from the NIT Raipur. Is thank you for your valuable input for the participants and for us, sir. Thank you, sir.
Okay, thank you very much, madam, for this opportunity. And I would also like to convey my thanks to participants for attending this session. Thank you very much. In case if you have any queries, please feel free to write me, and it will be my pleasure to answer your queries. Thank you very much. Thank you to everyone. Thank you.
Yes, sir. Thank you, sir. Thank you so much. Yes, you all. We have changed the small changes in our today's schedule. All of you are listening to me. Raise your hand.
Yes,
Yes,
ma'am,
ma'am.
listening.
Yes, yes,
Yes,
listening.
ma'am.
Yeah, we are preparing your question paper. The question paper is not too much hard. Do not worry about your questions and all. I'm again repeating again, because sometimes we hesitate what will be the questions in our test. So please, all of you, please appear for test is important. Okay.
Okay.
Ma'am, may I know the GCR code, ma'am? Google Classroom code.
We will post your all these things, in a chat box. The link for your test. Okay.
Okay, ma'am. Yeah, sure, ma'am.
Yeah. And we have, as per your schedule, we have planned from 3 to 4:30 as a pre-schedule. We have sent. So validity session will first. In that time, you will finish your feedback form. Feedback is compulsory. You have to fill in your portal. the participants login, you can see the one link is there for the feedback. So you, at the time of joining that validatory session, or before that also, you can put, because only the one session is remaining. Yeah, the one session will start from 12:45, and this is our meditation session. In between this also, you can put your feedback form. But filling the feedback is not the criteria only for getting the certificate. For getting the certificate is a criteria, the feedback as well as your test marks and your attendance. And I just listened to one news from my other coordinator. The 80% attendance is compulsory. Okay. So some relaxation also we are giving to you if you have attended one or two sessions in between. So we try our best for your attendance. We try our best for your test. Okay. So any questions you can ask.
Ma'am, feedback form will be shared from you, or we have to go for Atal portal feedback.
It's not go for ATAL. The participants, you have a login name and ID in ATAL website you have.
Yeah, ma'am, yeah.
You just go in that email ID and put your feedback in your participation link.
No, ma'am, I am asking about is there any additional feedback form you are providing, or that one only?
No, we are not providing any additional, but we will
Okay,
get the feedback, I think, the day after tomorrow. Okay. So for getting the certificate, the feedback is compulsory, the test is compulsory, you have to do, and the attendance is compulsory. But based on these all three, we will provide this one.
okay. Feedback we will do, but what will be the timing for test? It will be 1 hour or 1.5 hour.
Test we are planning to conduct from 3 p.m. Okay?
Okay, it
3
will start
to
from 3 p.m.
not
And
sorry, not three, not three. Three is a validatory function.
okay,
Four, yeah, four, 10 near about, because the validatory function will stop first, then
okay,
your feedback test will start. But feedback is not a online process. You do as a offline, because a test we will conduct. Okay, so in
okay.
meantime you fill your feedback form.
Okay, after 4 we will get our test link, and how much time will be there for test?
Not after four. Not after four. You join validity session. Validity session will end up. We don't know about the validity session because some of the speaker will give more times for completing this. So once it will complete, automatically your test will assign.
Okay, once you put your test link, after that how much time we will have to complete that?
We will provide 30 questions to you, and for 30 questions you have a 30 minutes. But 10 minutes
Okay,
pre and 10 minutes post we will allocate for submissions for link checking and all. Okay.
okay, okay,
Uh, Yesterday, I also told, because I need a 3 to 4 feedback from the participant side. But yesterday, I haven't got any name for the same. So please, anyone from your out of 100, provide me the name. They will give the valuable input as a feedback for our event, how we improve our event, as well as what are the challenge, what are the things you got as a better point of our event. You can mention in your the feedback. So in that time, in a validator session time, we will give 10 minutes for the feedback for the participants. Okay. So please kindly give your name. Dr. Geeta ma'am is here. Geeta ma'am. Aisha is there. Aisha ma'am. No one wants to give a feedback of our event. We are giving, we are taking too much pain for you, and you are not give any feedback, oral feedback to us, huh?
Okay, ma'am, I will give the feedback. No issue.
Okay. Sir, you just send in a WhatsApp group now your name, your college name, okay, and you want to give a feedback.
Okay, so how many,
In WhatsApp,
how much time I have
Ma'am,
to
in WhatsApp
go?
group only admin can post anything.
yes, sir.
WhatsApp group is disabled for users. Only admin can post there.
Okay. Participants are not able to process one. I will check, recheck. No problem. Okay, mine with you, no? My phone number with you.
Mrudu madam, I'll also give feedback, madam, if there
Yes.
is time.
Okay, just wait, ma'am. I just note down. Yes. The Geeta ma'am, ma'am, you are.
I'll be writing the details in chat box, madam.
No problem. You just give your ATAL ID. What we have provided to you.
It is not audible. Clear. 1 second.
We already provided that unique ID to you, na?
Yeah, 105, madam.
One.
105.
Yeah, I will take complete details from it. Okay.
Okay, madam. Okay, madam.
Even though you can have WhatsApp also, no problem. Yeah. And what about others? The one sir also told he is ready to give the feedback.
Yeah, myself, ma'am.
Yeah, Amrit sir.
Yeah, yeah.
Sir, your ID? Your
It's ATAL 003, ma'am.
003. Okay, thank you.
Okay.
Yeah. So we just close this session or any other query you just ask to me?
I have submitted the feedback in the ATAL portal. Okay, ma'am.
Yeah, thank you.
Morning, sir.
Is it possible for you all? You just mail to
Yes, sir.
me
Yes, sir.
because I'm not able to see that right now after completing this session, before completing
हाँ
this
जाएगा
session.
सर जाएगा सर वो
Rohit,
क्या नाम है
yourself?
आप बस मे भी परमिटेड लिख दीजिए यस सर यस
Yes.
Ma'am, when will be the next session will start?
So the time is same, 12:45?
12:45.
Yeah, 12:45 to 2:15.
Okay. After this, after 2:15, we'll give you the feedback.
In between also?
No. Whether you want to give the feedback immediate or after that session.
Yeah, they have lots of questions related to the best speaker.
Yeah. That is why we wait for one more session. Then after that, we'll provide the feedback.
But they are asking about the test also. But I'm saying again and again, do not worry about your test. We try our best for getting the certificate, which criteria you will fulfill. For that, we also try our best. Okay? That's why, yeah. So, could I close the session? Okay, thank you all. We again resemble at 12:45.
Work urgently.